Okay, my name is Alex Forshtat, and I'll talk about native account abstraction and our roadmap to achieve account abstraction endgame for Ethereum. So a quick reminder, what is even an account, what we are doing here. So account has four main roles in Ethereum ecosystem. First, it is your address, meaning it's your on-chain identity. It holds all your Ether assets, voting rights, whatever you do. And it performs an authentication of your actions. It uses a private keys you have and you sign your actions as the transactions on-chain, and account performs them for you. Account is responsible for paying your gas, because in Ethereum, whoever makes the transactions pays its gas. And account also performs the execution. There is a target contract that you are calling from your account. What we want to abstract is all four of those things, basically. So an address becomes an address of your smart wallet contract. The authentication is performed by the code of this contract that is deployed on-chain. And gas payment can be performed by a different contract that you specify as part of your transaction. And execution is done by your smart wallet contract, so it can interpret your inputs the way it wants. It can execute a batch, it can read some on-chain state, and so on. And where do we stand in regards of account abstraction in year 2025? So we actually already have account abstraction live, and it is built out of two components. One is ERC-4337. This is a protocol that is built on top of Ethereum. It does not modify Ethereum protocol itself. It has been live for 2 years now, since March 2023. And we recently released a new version specifically to target the new EIP, EIP-7702. EIP-7702 in turn does change the Ethereum mainnet consensus rules by allowing your EOAs to inject smart contract wallet code into their address. So the account acts as a smart contract for all intents and purposes. And it works great with ERC-4337. It can use paymasters to pay for EOA transaction gas. It can use bundlers to put the transactions on-chain in a decentralized way. And we are seeing quite a lot of adoption of these technologies already. So in 2 years, we have seen like exponential growth on account abstraction. We have seen hundreds of millions of user operations made by tens of millions of wallets across the chains we are tracking, and there are many chains we are not tracking. 7702 has been live for like 20 days now, but we are seeing a very good adoption rate, and it's probably going to be one of the most used EAPs in the future. So with all that said, what can we actually improve upon by achieving an endgame native account abstraction? So the first is obvious. We can improve our adoption rate. We can also minimize the attack surface of this solution, and this will increase our security. But one of the most important things, I think, is that current account abstraction solutions still rely on EOAs. So our bundlers, they must be an EOA to actually put your user operations on-chain. And 7702 accounts, while they do have code now, they are still fundamentally EOAs. They have a private key that controls this account. And one of the reasons this is very important is that EOAs do have an expiration date. Sometime in the future, we will have quantum computers, and EOAs use a cryptography that is known not to be quantum resistant. And we will need to replace them anyway. And we can also minimize the technical overhead and friction that we have in the current solution. So one thing is we are building account abstraction with the tools that are designed to build dApps, but account abstraction is not a dApp. And we have to cut corners to make things work on-chain and off-chain. And sometimes there are new EAPs, and they are breaking something for us, and we need to release new versions of entry points or bundlers to accommodate the new hard forks. And sometimes important new EAPs, for example, EIP-7805 that's introducing a censorship resistance layer for Ethereum, we cannot benefit from this EAP while being user operations that are not part of the native account abstraction. And last but not least, the gas efficiency. By using an on-chain entry point contract, we have like around 20,000 gas overhead compared to equivalent transaction done natively. One example of inefficiency I want to highlight specifically is bundler front running. So we are seeing it happening more. The way user operations work, you need to keep them secret, and a bundler needs to provide them directly to block builder to avoid being front run. And we are seeing more and more that, for example, on Polygon, Bundlers are not always able to do that, and MEV bots are successfully front-running them, meaning they didn't do the actual bundling, but they're getting all the profits from the ERC-437 bundle. Now that we talked about it, we can start thinking about the design of a native account abstraction solution together. So let's recap what are the on-chain contracts that are entities of an account abstracted transactions. So first is the most important one. This is your smart account. This is your wallet contract that's holding your assets and authenticates your transaction. But what if you don't have it deployed yet? In that case, you need to use an account deployer, which is a factory contract that will deploy the account on-chain for you. And what if you don't have gas to pay for this transaction? Well, then you need to specify a so-called paymaster contract, and this contract will look at your transaction and decide to pay for its gas or not, and it pays for gas. This contract is optional, but we are seeing that the vast majority of user operations are using a paymaster contracts and are actually sponsored. Now we need to provide some data to each of these contracts. So we are designing now a new transaction type. And for this transaction type, for Ethereum, we need to provide the addresses and inputs for these contracts. So we are defining the following fields for our transaction type: the addresses of a smart account that is sending your transaction, the data that is specific to this account, same goes for the deployer and for the paymaster. We don't define what you put in this data. It can be anything in any format. It can be a signature. It can be an init code for your account. It could be an ERC20 token approval using a permit function. And now we combine all these fields, and we end up with this transaction type. This is a new transaction type, and the new fields are in bold. So basically, all fields are new. Now that we define this transaction, we said that we want to validate this transaction using a deployed on-chain code. We are no longer using a consensus protocol to validate a transaction. We need to run some code. And that means that this code needs to have access to all of these fields. Now, previously, you had some limited access with origin opcode or call data opcode to the inputs of your transaction. But now we need more. So what we are introducing is a set of opcodes specifically to read your transaction input. We call them TX-param opcode family, and they are actually very similar to the call data opcode family, with minor difference. They are also accepting as an input the identifier of a parameter that you want to read. So to be specific, for example, if you want to read a paymaster data, we say that paymaster data identifier is 7. And then when you want to see the size of paymaster data, you do 7 TX param size. And then you can read this data into your memory by doing 7 TX param copy. And now, assuming that your contracts looked at these inputs, verified all of them, and are happy to accept this transaction, now we need to design a mechanism for these contracts to explicitly accept your transaction. We cannot rely on these contracts being called and not reverting, because you can reach a fallback function or some public function that doesn't revert. So you need to have some very explicit mechanism. And what we're adding is an accept role opcode. This opcode is very similar to return, but it takes one more input. It accepts the input as an input, a specific role that your contract agrees to perform during this transaction. So for example, if you're running a paymaster validation, the execution of this call would end with accept role paymaster validation. Very well. So now that we define these contracts, addresses, and roles, we need to give each of these contracts an opportunity to act on their transaction. And validate your transaction. So let's look how validation works for EOA contracts. So on top, you can see when you're sending a transaction from your EOA, it still needs to be validated. We need to check the signature of this transaction, its nonce, its balance, the gas fees, and gas limits. And all of it is done before your transaction is loaded or executed. This is done by the protocol, by the block builders. And then it performs one single big execution frame from your EOA to your target with your call data. Now, we have a more elaborate scheme for native account abstraction. Your transaction is actually split into up to 5 top-level call frames. So we start executing your specified contracts one by one. We deploy your account. Then we validate the transaction using that account. Then we validate that the paymaster accepts gas fees. And only after these 3 frames completed successfully and accepted their roles, we proceed to execution. And the critical part here is that if something is not valid, so meaning something went wrong during the validation frames, this transaction cannot be included on-chain. Like, this is different from a reverted transaction. EOA transactions can revert, but they still paid gas and they still got included on-chain. Invalid native account transactions are not inclusible on-chain at all. So how complex does it look like? The most complex flow that we can have looks something like that. You have up to 5 frames, as I said, 3 validation and 2 execution frames. I'll get to that later. And that means that the validation of your transaction now depends on Ethereum state and storage of the accounts involved in the validation. However, the transaction is no longer, validity is no longer defined by any cryptography as part of the protocol, and the cryptography is moved on-chain to the EVM layer. And of course, the simplest way, if you already have an account, if you are not using a paymaster, you will only have arrows 5 and 6, and only have 1 account in the flow. Now, speaking about like in a future version of Solidity, what this might look like, this is a pseudocode, this doesn't exist in Solidity. We could use a language feature, such as an annotation or some keyword for like payable, to specify functions that take a role in account abstraction. So users will not need to use the opcodes directly, of course. They would specify which functions are validation functions, which functions are execution functions, and they would use, like, for example, TX role parameters to figure out where they are located. And the example on the right is like imaginary terminal of Ethereum. If you try to make the legacy transaction call to this contract, you would reach execution function, and you would only run 1 log statement. But if you're doing a native account abstraction, by making a call to this contract, you have all the frames run. So you have validation executed, and then you have execution performed as part of your transaction. So there are 6 main components for transaction validity. The first 2 are same for EOAs and for native account abstraction. We check the balance and nonce. However, the balance is a balance of the contract that is paying for your transaction. So if you have a paymaster, we check the balance of the paymaster. If you have only account paying for transactions, that's one. But after that, it gets a little more complex. If you are doing your first transaction, you are deploying your account. We check the deployer contract accepted your role. After that, we check that your account is actually deployed. We check that your account accepted its role and performed the validation frame. And then if you provided a paymaster, we also let it check. And only if all 6 of these perform correctly is your transaction considered valid. So these are the main parts of native account abstraction. There are some technical details that we can dive into, and I wanted to highlight them. So one thing, paymasters get an extra frame. So you may know that when block builders execute an EOA transaction, first thing they do is they pre-charge the maximum possible gas cost of this transaction from your balance, and after the transaction completes, you get a gas refund. So we want to do something very similar with paymasters. So paymasters get a frame after the execution of your transaction to finish their bookkeeping tasks, to see how much gas you actually consumed. And it can also be used for a paymaster to observe the changes that your transaction made, and the paymaster may decide to revert your execution. However, do note, this is happening after the validation of your transaction, so the transaction is already included in a block and is paying its gas. Paymasters cannot retroactively refuse to pay gas for a transaction. And this frame also has access to environment variables that are unique for this frame, which is execution status and execution gas cost. And another aspect, we wanted to give more control to smart accounts over the validity of their transactions. When you sign an EOA transaction, it becomes valid, and it is valid indefinitely until you use the nonce. So the only way if you could cancel, theoretically, an account EOA transaction is to sign another transaction with a different nonce and send it first, maybe with a higher gas fee. we wanted to provide a way to invalidate transactions and provide the specific range. So we added valid from and valid until parameters to transaction payload. Next, I want to highlight how we integrate with EIP-7702 and also EIP-2930. So, of course, you can use native account abstraction together with 7702. You can provide an authorization tuple, as they call it, and you can use an EOA as a smart account, and your code will be deployed using EIP-7702. However, what brings these two EIPs together is they introduce a transaction payload that is a dynamic list of arbitrary data. And previously, there was never a need to observe this data on-chain, so this data remained available only before outside of the EVM. Now, we need to observe this data to validate the transaction signature. So what we are proposing is to provide the hash of these lists to TX param opcodes, so accounts and paymaster can validate the data. One more thing is the roadmap for migration from ERC-4337. So the architecture is very similar between these two proposals. So we expect only very minor changes between the application layer and all that. But we do require an on-chain update for accounts and paymasters. We expect that most paymasters will be able to just support both of these protocols for a foreseeable future during the migration period. And these protocols will probably coexist during this period. Bundlers, however, get a little bit different role. Bundlers will get even closer integrated with block builders, and they will provide account abstracted transactions to the block builders. I want to highlight EIP-7560. This is a very similar document. However, this is a roll-up improvement proposal. So this is a native account abstraction designed for layer 2 rollups. We were able to make it separate because we have two EIPs that reserve precompiled addresses and transaction types specifically for rollups. We cannot reserve opcodes for rollups. There aren't that many available opcodes. So we have two designs, but 7560, we do have an implementation of it for Geth and Aragon clients. And if you have a rollup or if you're interested in implementing it, you can do it already. And you don't need to wait for Ethereum Layer 1 to adopt 7701. Another document that I want to highlight, it is widely used now with account abstraction. It is ERC-7562. It provides a standard to sandbox the validation frames, and it prevents these validation frames from randomly invalidating or invalidating each other. And it is very important for block builders or bundlers to be able to validate multiple user operations or native transactions in parallel without a risk of mass invalidation. It's not a core EIP and it's not part of 7701, but it can be very helpful. Now, we obviously talked about quite a lot of complexity, and we are proposing this complexity to be moved to Ethereum Layer 1. And of course, we need to justify that somehow. We need to elaborate, can we actually remove complexity as well when we are adding native account abstraction to Ethereum? And I believe that we can. So first thing that is obvious, like ERC-4337 is becoming a bigger and bigger part of Ethereum, but it is a fairly complex mechanism. So by adding 7701, we can let it supersede ERC-4337. But looking a little bit further, more long-term, we can see that EOAs do have an expiration date. As I said, in around a decade, it is expected that quantum computing will become real, and then ECDXA cryptography will need to be replaced. And this can be a very painful transition for a blockchain. However, if we add 7701 now, we can deprecate EOAs in 10 years' time a lot more painless and easier way. And that goes with all the complexity of deprecated legacy transaction types, which we have like 4 of them. And we will not need to introduce a new EOA type specifically for a new cryptography. And specifically, EIP-7701 does not have any specific dependency on EVM. It does not require changes like a EOF or anything, and it can be ported relatively easily to any future virtual machine if there is a need to migrate, for example, a RISC-V. So yeah, I think that's it for me. Thank you very much, and happy to hear your questions.
I have two questions. One of them is the gas consumption of your modular validation logic. How expensive it looks like with modular stuff. It could be a little bit more expensive. That's what I'm thinking. You also talk about the front-running risks. I didn't realize how you are actually fixing that, because at the end of the day, the logic is going to be visible, and you need, kind of advanced cryptographic solutions to mitigate all this. Thank you.
Yeah, thank you very much. So about the gas consumption, the part where we have like on-chain entry point contracts that has to manipulate all of the user operations in memory on-chain, this is gone. So it's not replaced, it's just gone, and we don't spend this 20,000 gas on it. Additionally, we don't require actually the bundler signature anymore. So that is, let's say 5,000–6,000 gas that we don't need. So we are cutting all the excess gas consumption. This like simplifies it. So you only pay for gas that you actually consume. So your call data, it remains the same. Like the bytes you're putting on chain, this is what you are paying for. You don't have the wrapper around it. And because making multiple frames doesn't cost you extra because the call data is already there. It's already getting into memory. So you're just paying gas as you go. About the front running, like the specific mechanism of front running here. Yeah, a specific front running I'm talking about here is that the bundler collects all the user operations, and it has to include them in the block. But instead of working directly with the block builder, the bundler has to broadcast this bundle to the mempool. Now, with 7701, there is no bundle as it appears right now. Each transaction has its own validity, and there is no bundler that wrap them around. So you could front-run individual transactions, same you can front-run EOA transactions, but the bundler is not sending anything to the mempool. The bundler is presumably connected to the block builder the way MEV builder is connected, and like it cannot be front-run unless the block builder specifically chooses to rug pull it. Right, Yov?
Yeah, I wanted to add some. So yeah, regarding front running, as Alex said, there is no bundle to be front run. So if there is no bundle, there's no front running issue. But regarding gas consumption, actually we measured it. We wanted to see what would be the overhead of doing something similar to what you are doing with an EOA now. Like let's say you don't use any extra features like paymasters or special. So we wanted to see what would be the overhead of using such transaction type and having all these possibilities. So we implemented an account that behaves just like an EOA. It does EC recover on an immutable key, so no storage access, which means it's identical to validation of, and then it executes a token, like a token transfer. And the gas overhead, if I recall correctly, I don't remember exactly, but I think it was like 2,000 gas. It's like 2,000 gas more than it would cost you to do the same with EOA, which is, it's negligible compared to the value you're getting out of this transaction type. So it becomes really like gas becomes a non-issue, I think.
Yeah.
I have two related questions. One is that you say that an invalid transaction is not even included in the blockchain. So who absorbs the computational costs of having to validate and what bounds it? Because, it's a contract code that somebody needs to execute, and if it's not valid, then what happens? So it looks like an avenue of a denial of service attack. And the other question, which is a little bit related to this, is that back when we were discussing this stuff in the beginning of Ethereum of why we didn't have native account abstraction from the very beginning, was that even inclusion in the mempool is something that needs to be pre-validated. So currently on Ethereum, the conditions for validity are the nonce and the signature, which can be validated even before inclusion in the mempool. Whereas if you allow like Turing complete code to be executed just for that, on the mempool, it's not even clear whether by the time it gets to be included, it is going to be valid. So how do you protect the mempool for being
So the first question was about who validates it. So of course, the node that accepts this transaction in the first place will need to run the validation code. Like the validation code is limited. So you have like 100,000 gas, maybe. So like it's normally just an ECDSA signature recovery in the simplest form. So what like this is a cost that is comparable to what nodes need to do now, more or less, plus like storage lookups. If it gets more complex, the nodes can just decide on what they just don't want to accept. So if you get a native transaction with like 10 million of validation gas, it's very reasonable for a node to just refuse it without running the code. And this is one of the things that 75762 is defining. Like you should not accept transactions with more than a few thousand. And yeah, I think Yoav wants to answer the second.
Yeah, I wanted to give an answer about the mempool, about DOS, because that's like most of the work that we've been doing on 43.7, which also applies here. So the transaction has validation frames. Now each frame has its own gas limit. So let's say you are sending a 5 million gas transaction, but you only need 100,000 gas for validation, which is more than enough for almost any validation. So you're going to set the gas limit for validation to 100,000. And the mempool will have a rule saying that okay, we don't even accept, like, I mean, even though the transaction would be valid with any amount of validation gas, the mempool will not propagate it. So in the mempool, you limit the amount of unpaid work to a certain fairly low number. So that's one thing, is that I mean, you limit the amount of work. And the other thing is that the ERC 7562, the mempool restrictions, the mempool validation rules, apply many restrictions where the goal is to make the cost, the invalidation cost of a transaction high enough with an on-chain cost so that you cannot have a mass invalidation. You cannot invalidate a large number of transactions for free, which would be a DOS vector. So for example, you have things like you can't access any storage during validation. You can access it later after you agree to pay for the transaction. But until you pay the gas, you can only access your own storage slots or storage slots that are associated with your address, like a catch-up of your address with something, which is the way mapping works. This means that for each account, like in order to invalidate transactions for multiple accounts, you need to write to multiple slots. In addition, environment opcodes are banned. For example, you cannot check the block number or the timestamp during validation, because that would make it easy to have transactions that invalidate at the same time. So we have rules that ensure that it's order of n. Like in order to invalidate n transactions, you have to spend on-chain gas in the order of n. And this is the DOS mitigation here, combined with limiting the amount of gas spent.
Once EOA accounts are deprecated, what will be the approval mechanism for transactions? Because like even now, if we go to multi-sig or even to native AA implementations, like in Empire Wallet, right? It's still, in the end, there is still a signature by your private key.
Right.
So it still goes back to EOA, like in the end. And the second question, what will be the level of native programmability of access rights to account? Like who can do what, basically? Can we go to some really atomic level, so to say okay, if there is no transaction in 1 year from this account, then there will be this guy who can sign the transaction instead?
Yeah, I can answer that. So first, the post-quantum cryptography, it's an active research field, but there are signature algorithms that are not based on that are based on quantum-resistant assumptions. They are not based on elliptic curve or anything that is known to be broken by quantum computing in theory right now, but in practice, presumably in the near future. But this is we have years to do that. But I think the U.S. government, NIST, says that in 2030, the government should not be using pre-quantum cryptography, and they certified a certain number of cryptographic primitives to use. So I assume that this is what the contracts will do, but they will do it with their EVM codes. They will do it on chain. They will not need to introduce any of that cryptography to the Ethereum blockchain. And the second question, your validation is a Turing-complete code, so you can do basically everything, but it has a very, it is restricted if you want to use a mempool, as we just discussed. It is restricted to what kind of storage it can use. So as long as you keep the storage for this algorithm in your account, you can do anything, again, as long as you consume the amount of gas that block builders are happy to risk with, like just run the validation with the chance that it reverts in the last opcode after 100,000 gas and they get nothing for running this code. Then you can do the access control that you want.
Yeah, so basically that's why it's called account abstraction. We abstract it from the protocol to your code. So you can implement the dead man switch, for example, what you described. It's not something that the protocol will implement. We are agnostic to it. You can add this code to your own account as part of the validation function. You can say in the validation function, if the last transaction was more than a certain time ago, you can't check the time during validation because of the mempool rule, but you can return at a validity time, which the protocol will then enforce. So you can save the time in each transaction during validation, and then return, and then if another key is used, you can have an extra key that you give someone, and this key only works if the time between the current transaction and the last one is beyond 1 year. So this is something that is really easy to implement in your own account. That's because we abstracted it.
We're out of time, guys. Seems like Alex managed to wake up the crowd, but feel free to catch him after the talk and ask any additional questions.
Okay, great. We are
Applause.
Thank you very
Thanks,
much.
Alex.